Okay, so we're happy to have Fernando Quevedo to tell us about realistic string models and alpha prime corrections.
Okay, thank you very much, Matt. Well, thank you for the invitation to the organizers. Thank you. It's a nice conference, and I'm glad to be here and to see friends and good physics. And thank you for allowing me to give a presentation. Yes, I will talk about two different subjects. So the title is two different titles, just alpha prime corrections and realistic string models. So, and I apologize for that, but I thought it's based on these two papers that we have been working for a while, but they both came out last month. And I think they're both relevant for the content of this conference. So I decided to spend a little bit of time to each of them at the price of not being going into much detail. And upon my discussions, I will just also touch in two other papers from last year. Okay, so just to put you in the context, general approaches to string phenomenology, we have, sorry, I'm getting some things in my, are you getting some signs in the screen about the poll?
Yes, somehow the poll was popping up. I don't know what caused that.
That was an accident, sorry.
Okay, okay. And so model independent properties, so the effective theories from strings, model building for decompactifications, model stabilization and associative breaking, and cosmological scenarios. So my talk touches these 2 points, for the effective theories and the model building part. And I will start with the for the effective theories. And of course, both are relevant for the model stabilization issue. So let me start with the first paper. It's a paper, as I say, with Michele, Raffaele Savelli, Andreas Schachner, and Roberto Varandro. So we're trying to understand alpha prime corrections in type 2B compactifications. So that's the general challenge. So we know this is relevant because the Keller potential at tree level for the Keller moduli is no scale type, so that gives zero contribution to the scalar potential. So that means that the dominant contributions to the scalar potential are the corrections to the scalar potential. For n equals 2 supersymmetric compactifications, we have the leading order alpha prime corrections are computed by Baker, Hack, and Louis many years ago. And they are of order 1 over the volume cube. And they're the dominant ones. So, and they come because of the same, for the 10-dimensional case, they were alpha prime cube corrections were the dominant. And they have been playing a very important role in the model stabilization, in particular for the large volume scenario. They are key components of the scenario. So the question that comes out and has been for a while, are there in n equals to 1 compactifications, could they be the dominant corrections for this alpha prime cube of alpha prime to the 1 or alpha prime to the 2? That could be induced because there is orientive folding and so on. So this can be there. And actually, people had computed actually at the loop level, and they found n equals to 2, so alpha prime square corrections, and but they happen to be they give you a contribution to the scalar potential. It's okay, but when you plug that contribution to the scalar potential, give you also 0, like a leading order. So they're not that much relevant. And so the question is probably the most relevant is to see what happened to the n equals to 1. So the alpha prime to the 1. I have to apologize here that the terminology usually alpha prime expansion is probably not very precise. My collaborator Michele Ciccoli will not be happy if I mention it in this way, but that I think that's the way that people say it. Probably the best way to say it is in powers in the inverse volume that I will point out next. But that's the question. So the question is, are there corrections to the scalar potential, which are dominant over the ones that we know? So, of course, the question is very difficult, and people have been approaching this question for several years, the last 15 years at least. And there have been some corrections that people have found, and they have been either of the standard scale type or just shifts corrections to what we already know of the alpha prime cube, or subdominant. So in that sense, all the corrections people have been found, they have been finding, they are not dominant. So we try to just be as general as possible and see if we can extract information. So we use the standard scaling and shift symmetries of starting from the 10-dimensional perspective. And to simplify, we just tracked only the dilaton and volume dependence, because the dilaton counts the string loops, and the volume essentially it controls the alpha prime expansion. And they are the most relevant moduli to keep track of. And so in that sense, we simplify by only concentrating on these two fields. We use some MF theory dualities, try to see if we can extract some information from that, and concentrate only on the corrections to the scalar potential. So just look at what is it that contributes to the scalar potential, and not in general. So so we start with this 10-dimensional effective action at tree level. So and then you can see from this 10-dimensional action, you have two scaling symmetries. One is the one inside SL2R, and there's another one. It scales, and precisely having two scaling symmetries imply that you have two expansion parameters, two expansions, and one is the alpha prime and the other one is the loop expansion. So that happens for each of the effective filters of the 10-dimensional strings. There are different scalings, but there are always two, and that's a way of identifying the two expansions. And for example, for 11 dimensions, you only have one scaling symmetry, so it's only one expansion. Okay, and the leading order, as I say, is alpha prime cube. So you start with r to the 4 plus other terms, and plus dot dot dot. So in general, you want to have general corrections that we put in terms of MN, but that's identifying alpha prime and loop corrections, and you have power of the inverse dilaton, and curvatures to the arbitrary power, inverse metrics here, and the G, the antisymmetric tensors to power R. We could also have the F5, and there's nothing complicated about it. Just to simplify the notation, you just concentrate on these two expansions. And then you see how all the terms scales. Okay, so that's the 10-dimensional picture. In 4-dimensional, we can do that and use the superspace formalism in terms of e to the minus k over 3 and the superpotential. We can see how the corresponding compensator field scales, and then from that we can read how the Keller potential e to the minus k over 3 actually will behave at any order in the expansion of the alpha prime and the loop expansion. Okay, so look at the powers of the dilaton appear in both, so it's always complicated to keep track of it. And on top of that, in 4 dimensions, we know that there are the scalar potential. We also have powers of in DW, and that means the auxiliary fields. So there's an extra integer here, R, that counts that one. So in principle, you have coefficients NMR and this functions of R, M, and N. Okay, and this is already part of this paper that I mentioned from last year, and we have been exploring it in detail in this recent paper. So from here we can read, for instance, for different values of NMR, we can put 0, 0, 1, and we get the leading order correction, which is 1 over volume square, and that is this, the no scale. That's the coefficient is 0, so that's the no scale property. The alpha prime square, as I said, is also the 0. We have 2, 2, and 1. That will give you 0. For alpha prime cube, so we have 0, 3, 1, and then you get a coefficient which goes like 1 over volume cube. That's the BBHL corrections. And we have the question if alpha prime to the 1, that will contribute volume to the minus 7/3. And that's what I say is will be dominant over 1 over volume cube. And if this has been playing an important role for model stabilization, this would change completely the picture if they were there. Okay. However, we will prove, we have argued that essentially we prove that they're non-present at the string tree level. Okay, so more generally, we computed using for all this expansion metrics and so on. We have the different contribution from 10 dimensions and different versions for the potential dependence on the volumes and how the thing that appears here. You can see the dominant part start with volume to the -3 and so on at tree level, at string tree level. This is not a great result. It's not a big result, but it's important enough because we say that, okay, this alpha prime, this 1 over volume to the 7/3 may be there. Probably they are not there, but if they are there, they are suppressed by loop correction. So that means that the 1 over volume cube can always compete with both with that one because they are two different expansions. So in that sense, actually, you can use this 1 over volume to the 7/3 if they were there as a way to get an uplift. So in that sense, it's good news for the current status. Okay, but beyond that, we had to resort to more general scenario, and then we have to use F and M theory dualities, and so this complicated picture here that we have of the different dualities from M theory and F theory, that at the end you compactify on a fourfold, elliptically fiber fourfold, and then go to the what is called the F theory limit to get information about the four-dimensional effectivity theory. So it's playing with the scaling of both sides on the fourfold and the threefolds and so on. We can try to extract informations from that. I will go quickly because now I can see the time is running. But from doing that in general, we have the fourfold. We write it as a general fibration, which you split the Carrier potential at the base and a fiber piece. And the base only depends on the set coordinate, which are the base coordinates, and the fiber depends on both. And from that, you can extract the fact that there are no alpha prime to the odd powers from standard dimensional reduction. Okay, that means that we are missing something because there will be the alpha prime cube should be there, and they should be coming not from standard dimensional reduction but from loops. And I will just show that I will skip this because of time concern, and then move to the next part of my talk because I'm checking my time. I have 10 minutes only. 15 minutes. Okay, so this is the second paper, and this is addressing one question that we have been thinking for a long time. It's just, can we get something very close to the standard model from string theory? And as we have seen from this conference and others, that there are plenty of models which are very close to the standard model, quadrillions of that in F theory and so on, as we will hear probably from Medium, and we have here in the past, and heterotic also, as Peter mentioned. But all of them have the problem of having not dealing with the modular stabilization piece. So in that sense, we're addressing that piece to construct a realistic model, and again, the standard model Quevedo say, with a stabilized Calavillado. So and this is the work with, again, with Michele, Iñaki, Andreas, Pramo de Chucla, and Roberto Balandro. Okay, so this is following up a program that we started 20 years ago with Aldazabal, Ibanez, and Oranga. You said, well, if you can have the standard model on D3 branes at singularities, you can have chiral states there, and then you can ask if you can have something realistic, and just concentrate on the duality, on the singularity first. And once you have everything, you have a realistic enough model, you can embed it in a proper Calavillado, and then see if you can have a proper global model. So that was the philosophy that we call bottom-up approach at that time. It is actually a modular approach. So we have 3 stages: construct a realistic local deep brain model, then forget about the deep brain, just do global issues like modular stabilization, like KKLT and LVS that have been developed and very successful in the last 15 years. So see breaking, the Sitter, inflation, and so on, and then combine the two to get something as realistic as possible. So each of these steps, even those are far simpler than just trying to do the whole thing by itself, each of them is very challenging, and that's how that we try to do here. So there's a long history of branes at singularity that I will not go in detail, but I would like to emphasize this paper by Weinhold in 2007 that I think is a very, very, very interesting paper that I personally had overlooked before, and I think is crucial to get something as realistic as possible. So these constructions are based on Del Pezzo singularities, that you have heard before. So it's essentially dPn is a blow up P2, so it's a surface for the force real dimensions with n endpoints, which are blow up. And you have the host number here and so on. And with you, the important thing about the pesos is that you can just contract to one single point. So, and they can be divisors inside the Calabi-Yau, and you can have that component to shrink to one single point. And and in the singularity, then you can have say D brains, and you can have a quiver like this one. This is the simplest one, DP0, and you have the three nodes, and then you have by fundamentals connecting the nodes and UN groups in each of the nodes. And you can even compute the superpotential using dimer techniques and so on. So all this is well known. And actually the D-brains can be actually this thing as you can have a fractional Fi brains as bounded state of other D-brains when you blow up the singularity, and then this one will include the 7s, the 3s, and the 5s with the corresponding charges. And then people say, well, we can ask the question, what will be the minimal standard model quiver for which we can aim at? And people came out with a diagram like this, but you have the standard model gauge groups and with different bifundamentals. This essentially generalizes the old paper by Ibanez, Marchesano, Rabadan, but it was put here in this context by Bernstein and Pinansky in 2006. The question is, can we derive this from string theory, from nodes and singularities? And the answer is yes. and you can start with a Del Pezzo 5. Sorry, I skipped one slide here. Well, so the slide is gone. So I can say you can start with Del Pezzo surface, Del Pezzo 5 singularities. So Del Pezzo 5 will have 8 nodes, and you can have the UNs on the different nodes, and you can judiciously choose the rank of the gauge groups such that at some point you can do the Hicksing. And for instance, you have here a U6 and here a U4 plus M, and here a U4. This U4 and U4 here, when you Higgs this corresponding by fundamental, you will collapse this two to one single node. So the U4 will disappear. But you will have the UM. But you have a U6 and a U4 here. You will have a U2 remaining there. And this U2, with the extra n components of this by fundamental, you will have, since it used to be a 6, m, now you have 2 plus 2 plus 2, m, and then you have 3 families. Okay, so that's the easiest way to see it, and you can see it in a more sophisticated way in terms of bounded states of brains, and then you can get a quiver, which is now closer to the one that we had for a standard model, with UM repeated here and U2 here. Okay, so this is the corresponding gauge group. Okay, that is. But you have giving best, you have Higgs, and you have to make sure that the D-flatness conditions are satisfied, which are all satisfied for the non-abelian and abelian groups, including the anomalous U1s. And then you have to worry about F-flatness. F-flatness, you have the superpotential also computed, but then these conditions are more difficult to satisfy. And I come back to this later on. But now to get to what is the standard model quiver, one property that you can see from the standard model quiver here is that it is not oriented. So you can have in all the pets and so on, all the arrows go in the same direction, whereas here they do not. Okay, and so that's perfect for orientifolding. So you can start with the remaining quiver we have, we orientifold it, and then we are left with something unoriented. And then this one looks already like the standard model, like a left-right symmetric and so on, with the corresponding Higgses that allows you to get to the standard model quiver. Okay, so essentially, you can, starting from a Del Pezzo singularity, 5 and above, you can get to to the standard model quiver in that way. Okay.
You have about 5 minutes left.
Thank you. Now the question is to embed this on a Calabi-Yau. And so you have to say a Calabi-Yau and put some constraints. You have to have Del Pezzo divisors with this constraint, you want to have also diagonal del pezzo, because you want the del pezzo to be shrinkable by itself, but not shrinking something else. So it is, this is, you have these constraints to be satisfied. These are the intersection numbers of the corresponding Calabi-Yau. So they have to satisfy this constraint to get this diagonal del pezzo. And you have involution, as I say, we need to have an oriented folding because getting from n equals to 2 to n equals to 1, but also to get this standard model Quevedo, we need an involution. So, and we may have O7s or O3s. If you have O7s, then you are forced to have D7s. And D7s are very good because they can wrap a large cycle and produce what we have T-branes. And T-branes are the ones that you can use to do the uplift. You may also have O3 planes, and for that you may put on their anti-planes. We haven't done this yet here. And you have to satisfy all the tadpoles conditions and anomalies, like a Fred-Witten anomalies and so on, cancel. So this is a non-trivial condition. And ideally, you want to have another diagonal del pezzo or another del pezzo to have an perturbative superpotential to stabilize the modeling. And we search for those Calabi-Yaus and in the Kreutzer-Skarke database. Unfortunately, we couldn't find any of that satisfying all these conditions. And so we have a conjecture that actually there are none in this. And so use diagonal del pezzo, we can find any of them. However, we didn't stop there, but we went to complete intersection Calabi-Yaus, actually with two polynomial conditions to restrict the Calabi-Yau. And in that we found examples, and this is a cartoon that Andreas did for me. You have the Calabi-Yau, you have the brane at the singularity, you have the stacks of the D7 branes where you will have fluxes and that are required also for consistency, and that will give you the uplift. And then you have other 2 4 cycles where you can have Euclidean D3 branes, and there could be like instantons. You have to make sure that you can have instantons to control the chiral states and so on, to be able to have the instantons, and we have them. And with that, you have a model stabilization. You can have a expression for the overall volume. This has total superpotential with the flux part, the quiver part, and the non-perturbative part. And then you look for the scalar potential. The leading order, volume order 1 or volume square, you have the standard GKP for fluxes for the dilaton and the U moduli. But then you also have now the part from the quiver that has to also to be 0. And then you have D terms. On D terms, you have 2 D terms, one from the quiver and one from the D7 branes. The one from the quiver, it so happens that the charge piece cancels automatically. So that tells you that the Fayet-Leopold is 0. And that's interesting because that gives you that the modulus is stabilized at 0. That's the size of the cycle. So it came out dynamically to be stabilized at 0. Whereas for the D7 branes, actually it's not true that you have the corresponding matter fields and the D7 brane. This is the Fayet-Leopold, so they have to be satisfied by phi square equals to this 1 over volume to 2/3. And that's 1 over volume square order of the potential. Then you go to the next order, you get the standard large volume scenario piece, which is the 3 terms with the 2 non-perturbative ones and the alpha prime correction. And on top of that, you have the soft term for this phi field that has a VEV, and then it will give you something of this order. So you combine both, you have the LVS plus this term. So this term is that what you use to uplift. And that's the give you model stabilization as in the LVS. And this can be interpreted in terms of what is called T-branes, as we did with Michele and Roberto several years ago. Okay, so you can use that and find a minimum, which is essentially Minkowski, just to get the uplift to the CT. However, this is where the good news stops. The volume, we get it large, but not as large as we want. We get 10 to the 3, 10 to the 4, 10 to the 2, 10 to the 3, but not much more than that. And if we increase the number, the want to increase the value of the volume, we have to have the potential very, very, very small. And that's not impossible, as we heard from Lian earlier this week, but I think we will have preferred if we get something smaller, and we are working on that at the moment. But also you can explore associative breaking. The interesting thing is also as since the volume, the modulus is stabilized at 0, the singularity, then you don't break supersymmetry on the brane. So you must think that you won't have sequestering, and that may be still the case. However, Joe Connon and collaborators considered this case in the past in general, and they found that there is usually some logarithm redefinitions of the corresponding modulus, and that may affect the corresponding F term, and you may have still corrections, a contribution to the F term for the corresponding modulus. If that is the case, then you have large-scale Susy breaking with the gravitational mass, which is very, very heavy.
So you're starting to cut into the question time now. Oh, good. Here's conclusions. Okay.
So essentially, we have made progress on the systematic understanding of corrections to the moduli potential, and in particular, as I told you, the alpha prime to the 1, we managed to prove that they are not there at tree level, and there may be more, but we're trying to have a more systematic understanding of all the corrections, and I think these techniques we are using can be very useful. And then we found, but I say, this is a very realistic model. When we have actually the Quevedo of the standard model with the modular stabilization in Calabi-Yau, and of course you can get the uplifting and get a de Sitter model. But as I say, we get volumes which are not ideal in that sense. This depends on the parameters of the Calabi-Yau. So I'm sure there will be many other examples where things will be better, but we have to improve. So open questions. We need to get better understanding of this FM theory picture to get what we call this quantum correction. So to understand better all the alpha prime to the n corrections. Ideally, we would like to use all this for F theory model stabilization. For the realistic models, systematic search. Now we have all the ingredients to do a systematic search. In principle, that is something can be done. Also, we can include the anti-brain uplift. We did it only with the T-brains, which were simpler, but in principle, we can engineer a Calabi-Yau where we have all 3 planes, and then we can have the anti-brain uplifting, as we did recently with Roberto and Chiara. And also to address phenomenological issues. We have this quiver there. We have to address issues of flavor, neutrino masses, proton decay, that which are local issues, as Peter was mentioned. So I think it will be an interesting things. And easily we can add more moduli and consider the possibility of getting inflation from this setup, which I think that would be very interesting to get. Okay, so I stop here. Thank you very much.
Okay, let's all thank Fernando for the nice talk. And we have time for probably one question. We have just a couple of minutes. So Alon, what's your question?
Well, thank you, Fernando. Can you hear me?
Yes, very well. Yes.
Right, because I'm using my laptop on Windows, which I don't usually use. Okay. But so we in the past we constructed, you can stabilize moduli with asymmetric orbifolds, and you can stabilize all, say, geometrical moduli. And we constructed models in which we argue that all moduli are stable, but we found that they would be very special in the sense that they will have quite violent twisting or asymmetric twisting of the internal dimension, and the gauge group would have to be standard like model gauge group. So do you find something similar that in Vacua, in which first can you use asymmetric twisting in your construction, and second, are the cases with stable moduli, are they special, are they generic? What do you think?
No, it's a good question. Yes, no, asymmetric twisting, no, because I mean, it's a different approach. So it's not just an orbifold, it's just a structure of the similarities itself. And then let me see, what was the other question?
Do you think that these are where you can say stabilize? Are they special or are they generic?
No, but that's a good point. For the thing that for instance, the fact that for me was a surprise that we were expecting the singularity modulus to be stabilized at a small value. Of course, it has to be valid in the approximation. You have to span around 0, so it has to be smaller than the string scale. But it ended up to be exactly 0. So the conditions were such that the matter fields and so on, that actually the Fayet locus was exactly 0, and that means that the modulus is 0. So in that sense, it looked that the singularity was an attractor for a solution. But for all the other moduli, is the standard GKP, KKLT, or LVS picture that we have all these fluxes and so on that will give you all the freedom to stabilize them at different values.
Thank you.
Recoupling and so on.
Okay,
Thank you.
so let's thank Fernando again, and now we can